Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be taking a look at how to convert between degrees and radians of angle measures, how to graph the angles in standard position, and how to specify the quadrants that the terminal side lies in. Don't forget there are tons of support resources at mathgotserved.com, or just take a look at the links in the description below for links on how to gain more assistance in your math learning. All right, to get us started, we're going to take a look at the definition of what angles are. So let's go ahead and write this down. So how can we define angles? All right, so the definition of angles is as follows. So you can define an angle as the inclination, okay? An angle is the inclination or tilt of one, you could call it a ray or segment, okay? Ray or segment. This particular ray or segment we can refer to as a terminal side. All right, think about terminal as end, so the end inside where you end up in. All right, when you start to tilt. So an angle is the inclination or tilt of one ray or segment, the terminal side, from another ray or segment. Okay, this ray or segment that you're tilting or inclining from is called the initial side. All right, and these two are happening relative to the same point of origin or intersection, relative to the same point of origin or intersection. All right, so let's give ourselves a graphical representation of what we're talking about here. So we're going to depict the angle in standard position. Okay, so let's say we have a coordinate system. All right, and then you have a ray. We'll call it the initial ray. All righty, so you have the initial ray starting from the origin and going to the positive x-axis. So let's call that the initial ray. All right, initial ray. All right, so what we're going to do now is we're going to create an angle. We're going to create an angle by starting from that initial ray. We're going to have a tilt or inclination from that in one direction or the other. All right, so let's go ahead and create that angle. So starting from your initial ray, you have a tilt or an inclination. You see what's happening right here? So when you're rotating away, relative to the same, they have the same point of origin, right? So you see that right there? This ray right here that is tilted or inclined from the initial ray, this one we can call the terminal or end, terminal ray. All right? Terminal ray. Now the tilt or inclination, this region swept between these two rays with the same point of origin, this is what you refer to as the angle. All right, so there goes your angle, ladies and gentlemen. And now let's call the angle theta. All right, so theta right here, this symbol is a lowercase Greek alphabet called theta. All right, theta is a lowercase Greek alphabet and is customarily used to represent angle measures, okay? For representing angle measures, because a lot of contribution to the development of angles and trigonometry and geometry all originated from Greece. So giving them credit by utilizing their alphabets for critical components or representations in trigonometry. All right, so this is a graphical representation of what an angle looks like. All right, so another terminology that's extremely important to know is quadrantal angle. Quadrantal angles basically helps give us a reference frame. So when you're graphing an angle in standard position, your quadrantal angles can help you determine where to position your terminal side. All right, so let's define what quadrantal angles are. So a quadrantal angle is an angle graphed in standard position. So basically on a coordinate system, is an angle graphed in standard position whose terminal side lies on one of the axes. All right, that's exactly what quadrantal angles are. All right, so what we're going to do is we're going to take a look at positive and negative quadrantal angles. Let's start with positive quadrantal angles. So let's say that you have your coordinate system right here. So we have the intersection of the x and the y-axis, and guess what? These rays starting from the origin right here, they form your quadrantal angle. Okay, so this is your x-axis, and this is your y-axis. So when you start from the positive x-axis right here, this is known as 0 degrees. So the ray that falls on top of this angle right here, that's known as your 0 degree quadrantal angle. Okay, and now what we're going to do is we're going to draw the next one. If we rotate 90 degrees, it takes us to the next quadrantal angle. So what you want to remember is that the direction of rotation impacts the sign. All right, when you rotate counterclockwise, that's known as a positive rotational direction. And then when you rotate clockwise, that's the negative directional angular rotation. So we're just going to do positive right now. Okay, so for positive, if you start from the 0, the positive x direction, and you rotate 90 degrees counterclockwise, it takes you to the next quadrantal angle. So this one is 90 degrees. Every quarter of a circle rotation is 90 degrees. And then when you rotate another 90 degrees, you add 90 degrees there, it will take you to the negative x axis. Now that one is 180 degrees. So going from 0 all the way here, 90 plus 90, that's 180. Okay? And then when you rotate again another quarter of an angle, takes you to the negative y. That's another quadrantal angle. This one is 270 degrees. And then when you rotate another quarter of a circle, or 90 degrees, you have full circular rotation, right? So this is 90 degrees here. And now another 90 degrees takes you full circle, and guess what? You have 360 degrees. When you have two angles overlapping like this, 0 and 360, they are referred to as coterminal angles because they terminate at the same ray. All right, so these are coterminal angles. So just remember, every quarter of a circle rotation is 90 degrees, and full circle gives you 360. These angular representations can also be written in radian format, but degree format is easier to visualize. So we're just going to convert these to their radian equivalent values, and then we'll talk about how to convert them in the examples that we'll do subsequently. Okay, so 90 degrees in radian is pi over 2 radians. 180 degrees, half a circle, is pi. And then 270 degrees is 3 pi over 2. And then full circle 360 degrees is also equal to 2 pi radians. Okay, So these are the radian equivalent of your positive quadrantal angle. And then you can keep going around and around and around and round and over. Okay, so remember you add 90 degrees or pi over 2 repeatedly in order to generate your quadrantal angles. Now let's take a look at the negative quadrantal angles. Alright, so we're just going to follow the same pattern, but our rotation will be in the opposite direction. Alright, so let's sketch the negative quadrantal angles. So what we're going to do now is we're going to start from 0 degrees. So the positive x-axis is your 0 degree angle. Alright, that was the first one. Now remember, the direction of a rotation impacts a sign. When you go clockwise, it's the negative direction rotation. Alright, and then if you go counterclockwise, that's a positive rotational direction. We're generating our negative quadrantal angles in this graph, so we're going to be going clockwise. Alright, so when you start from here, start from 0, and you rotate quarter of a circle in the clockwise direction, guess what? That is negative 90 degrees. Okay, so this negative direction right here, the negative x axis, is the first or the second negative quadrantal angle. So this is negative 90 degrees right here, negative 90 degrees. Rotate in this direction, in the clockwise direction, so that's negative 90 degrees. You rotate another quarter of a circle, right, subtract another 90 degrees. That will take you to negative 180 degrees. Rotate another quarter of a circle. Let's change the color here. That will give you negative 270 degrees. Alright, and then if you rotate another quarter of a circle, keep subtracting 90 degrees, that'll give you the next negative quadrantal angle. So subtract 90 degrees, and that is negative 360 degrees. Alrighty, so there goes your negative quadrantal angles. Let's write here radian equivalent. So this is negative 90 degrees, which is the same thing as negative pi over 2. This is negative 180, which is the same thing as negative pi. And then this is negative 270, the same thing as negative 3 pi over 2. And then a full circle, negative 360 is the same thing as negative 2 pi radians. Okay, so just remember there are two ways to represent angles. Degrees, which is more ancient, and then radians, which is more modern and used extensively in higher level mathematics. Before we move on, just one last thing that I need to highlight and that we'll need for the examples we're going to be working on are the quadrants that the angles lie in. Okay, so if you lie between 0 and 90 degrees, that's quadrant 1. Alright, you start from the 0 and then that's quadrant 1. Between 90 and 180, this entire region is quadrant 2. This is quadrant 3. And this is quadrant 4. When we're dealing with trig functions, the quadrants are extremely important in determining the sign of the angle that you're evaluating the trig value of. Okay, so it's very important to know the quadrants. So the quadrants is agnostic to the direction of rotation. It's always 1. Is always 1 following the direction of the positive. 1, 2, 3, 4. So you basically name the axis by rotating in the counterclockwise direction or in the direction of the positive orientation. All right. So even though your angle is negative or positive, just remember the quadrants do not change. This is always 1, 2, 3, 4. 1, 2, 3, 4, whether it's positive or negative. Okay, so let's keep that in mind, and now I'll take a look at some examples. Alright, so the instructions for the examples that we're working on are for us to express the given angles, express the given angles in degree and radian forms, degree and radian forms. All right, then so graph it and specify the quadrant. Graph the angle and specify the quadrant. Specify the quadrant. Okay, so let's take a look at the first one. Let's say we have, for number 1, theta, the Greek alphabet theta, is equal to 60 degrees. All right, so we're going to start by expressing it in degree and radian form. So what is theta in degrees? So in degree form, guess what? Theta is 60 degrees. It's already in degree format. Okay? So no conversion needed here. How about in radian form? What is 60 degrees in radians format? In radians, we're going to apply the appropriate conversion factor. All right? So let's talk about that real quick. Your conversion factors are what you use to convert from degree to radians, or the reverse, are you either multiply by pi over 180 degrees, or you multiply by 180 degrees over pi. All right, so the secret here is you look at what you're given, the conversion factor that has that measure either on top or on the bottom. The conversion factor that has it in the opposite orientation or position is the one that you use. Okay, so for example, we have degree upstairs here. The one that has degree in the bottom is the one that you use. So we're going to be using this one. All right, so the first one converts degrees to radian, and then the second one converts radians to degrees. So let's show you the computation here. So for radians to degrees, we're starting with 60 degrees, right? So we're going to pick one of these two, but the one that cancels out the degree. So if there's degree on top, pick the conversion factor, one of these two that has degree on the bottom. So it cancels out. So we're going to pick the first one. You see this, 180 degrees and pi. Pi and 180, remember, are exactly the same thing. All right, so you're basically multiplying by 1. All right, one is just in radians and the other is in degrees. Now we oriented it like this, so observe this. See how the angles, the degrees cancel out? What we're left with now is radians. Okay, so whatever conversion factor you're picking, make sure that it's the angle measure is in the opposite direction of the angle that you're given. All right, so now let's simplify this, or we can cancel out. 60 goes into 180, right? So 60 goes into self once, and it goes into 180 3 times. Multiply across, you're going to have 1 times pi over 3 radians as the radian measure. All right, so theta is equal to 60 degrees, or theta, exactly the same angular measure in radian form, is pi over 3 radians. Okay, so now let's go ahead and graph it. The angle in standard position is just a sketch. Okay, we're just going to sketch the angle. All right. Or we just want to see, do we get a general idea as to where it's located? So now we're going to make use of the quadrantal angles to help us orient the position of the terminal side. All right, so can you visualize where this angle 60 degrees of pi over 3 is? So what we're going to do is make a sketch. So starting with 0, we're graphing the angle in standard position, starting with 0. Since the angular measure is positive, that means we're going to be rotating in the counterclockwise direction of rotation. We're going to be going up. Okay, starting from 0, you go up, that's positive. You go down, that's negative. So if you go quarter of a circle, that will take you all the way to 90 degrees. Do we keep going, or do we have to back up? we definitely have to back up because 90 degrees is greater than 60. Okay, so the terminal side that we want, starting from 0, if we go quarter of a circle, that's 90, that's too big. So we're going to back up. Halfway is positive 45, right? So it's a little 60 is a little bit bigger than 45. So we just rotate it up like this, kind of sort of like that's is a sketch. All right, so this angle that we just graphed is theta. All right, so this is theta, and its measure is 60 degrees, or is also can also be written as pi over 3 radians in radian format. Okay, so what quadrant is it? This is quadrant 1, 2, 3, 4. So theta is in the first quadrant. So theta is in quadrant number 1. All right. So now we're ready to take a look at another example. So for question number 2, let's say we have the following situation. What if we had theta is equal to negative pi over 6 radians? So theta is equal to negative pi over 6 radians. So let's do a negative example this time, and also one given in radian measure. All right, so the same set of instructions, we're going to express it in degree and radians, and then sketch the angle in standard position. All right, so what is negative pi over 6 radians in degrees? So in degrees, well, we're going to apply the appropriate conversion factor. Okay, let's do our scratch work on the side here. We're given pi over 6, and we want to pick one of these two to carry out our conversion. All right, so notice the angle that we're given has pi on the top, so we're going to pick the one that has pi on the bottom, so it cancels out. So we're going to multiply by the second one. All right, why is that? Because if we multiply by 180 degree over pi, you will notice that the pi's are going to cancel out nicely. Take out that radian angular measure, and you're left with 180 degrees over 6. Okay, now how many times does 6 go into 180? 6 goes into 180. 6 goes into 18 3 times, or it goes into 180 30 times. All right, so you could do it that way. You could cross reduce, or you could just multiply 180 degree over 6, and then when you divide it out, 6 goes into 18, bring down to 0. 30 degrees is your degree measure. Okay, so for this problem, theta is equal to 30 degrees. Now, what is the radian equivalent? Well, the original problem was given to us in radians, so we don't have to do any work for that. So 30 degrees can also be written, I'm sorry, negative. Let's not forget the sign now, because there was a negative here. Negative, negative. So negative 30 degrees is the same thing as negative pi over 6 radians. All right, now let's go ahead and sketch the angle in standard position. All right, so if you want to draft this angle negative 30 degrees, we're going in the negative direction of rotation. Which of these units will you use? Are you going to go with the degree format or radians? Which one is easier to visualize? Well, we're going to use our quadrantal angles to orient ourselves. So it's easier to use degrees because it's easier to visualize quarter of a circle, right, in degree format, as opposed to radians that's given to us in a fractional notation. So we're going to be rotating counterclockwise. Remember, when you go down, that's negative. When you go up, that's positive. All right, so we're going to be rotating downwards like that, and that's a negative direction. All right, so we're looking for 30 degrees. If we rotate quarter of a circle that would take us all the way to negative 90. Do we keep going or do we back up? We definitely need to back up, right? Because negative 90 is smaller than negative 30, okay? So if we start from 0 degrees, okay, and then we rotate 90 degrees, that's negative 90. But we need to back up because it's too small. Halfway is negative 45, so it's negative 45 is smaller than negative 30, so back up a little bit more. So around there, that's where our terminal side is. So this is theta, okay? And then this angle that we just graphed is 30 degrees, negative 30 degrees, or negative pi over 6 radians. All right? And what is the terminal side? What is the quadrant that our terminal side lies in? So this is 1, 2, 3. Remember, enable the quadrants in the counterclockwise or directional rotation. Doesn't matter if it's up or down. It's always the same. 1, 2, 3, 4. We can see that the terminal side lies in quadrant 4. All right? So theta lies in quadrant 4. All right, so that's how you convert between degree and radians, sketch the angle in standard position, and specify the quadrant.